All right, so this is part two, deriving the S4 character table. Where we left off last time was that we figured out the first two irreducible representations. First one was totally symmetric representation, so it's ones across the board. We used the z function to figure out gamma 2, see how that transforms. And when we transformed x, we found out that x and y transform together, that the transform is 2, 0, minus 2, and 0. It turns out, though, that what we also figured out is that one of the rules of our character table wasn't being satisfied, and that is that the total number of symmetry operations or order of the point group, which is 4, right? We have one symmetry operation in each class here, 4, wasn't equal to the sum of the squares of the dimensionality or the characters underneath the identity operation. So 4, in other words, 4 is not, for the order of the point group is not equal to 1 squared plus 1 squared plus 2 squared. And so what this tells us is that gamma 3 actually isn't a reducible representation, but rather it's a isn't a irreducible representation or vector, rather it's a reducible representation. And so this can't be actually our final correct answer. And whenever this happens with these basic functions like x and y, what it tells you is that we have to break up this function into two actually irreducible functions. In other words, this has two components. And what's going to end up happening is that some of our values here that we end up figuring out are going to have imaginary or complex characters. So the only way for the math to work out here is to invoke, imaginary complex numbers. And so what we're doing is we're breaking up this gamma 3 into gamma to two components, which are actually going to be gamma 3 and gamma 4. And then we will have that 4 equals 1 squared plus 1 squared plus 1 squared plus 1 squared, right? Because this we're actually eliminating and instead decomposing into these two components. All right, so we don't know what these two components are, but we know that they will sum up to equal 2, 0, minus 2, and 0. And we know we can call them some arbitrary numbers. Let's say variables A, B, C, and D, E, and F. And what we do know is that just like any other irreducible representations, these irreducible representations will be orthogonal with all the other irreducible representations. That's the great orthogonality theorem. So gamma 1 dotted with gamma 4 will be equal to 0. So another way of writing that is that, well, gamma 1 is 1, comma 1, comma 1, comma 1. And the gamma 4, this first component here, is 1, A, B, C. So that must equal 0. Remember, this is adjusted for the number of symmetry operations in each class, this orthogonality. So we have this whole thing also timed by one symmetry operation, one symmetry operation, one symmetry operation, and one symmetry operation. Well, we're multiplying by a bunch of ones in this case, so it doesn't do anything. So we dot product this out, and this gets us that 1 times 1 is 1, 1 times A is A, 1 times B is B, and 1 times C is C, that this must equal 0. And then we can do a very analogous thing with gamma 2, dotted with gamma 4 equals 0. Gamma 2 is 1 minus 1, 1 minus 1. And when we dot that with 1, A, B, C, right, that also must be equal to 0. We're going to get now 1 minus A plus B minus C equals 0. And what's really nice is if we add these two equations together, the system of equations we get, well, 1 plus 1 is 2, A plus negative A goes away, B plus B is 2B, and C plus negative C goes away. So we get now this very easy equation, which tells us that 2B is negative 2, and B must therefore be equal to negative 1. So we can we solve for this B component now. This is negative 1. Now, the interesting thing is that everything that we just did is also true for the bottom component, right? 1, comma D, comma E, comma F. So we could go ahead and write the exact same system of equations, but now putting 1, comma D, comma E, comma F instead of 1, comma A, comma B, comma C. If we did that, we'd find the exact same thing, but now not B equaling to negative 1, but d equals to -1. So we know e equals -1, sorry. So we know b and e here are both equal to -1. At this point, we need to use some other character table rules, and you can see my video on imaginary characters, but there's a general rule for any irreducible representations, which says that the um, sum of the squares of all the characters of the irreducible representations multiplied by the number of operations in each class equals the order of the point group. Uh, so for example, 1 squared times 1 plus 1 squared times 1 plus 1 squared times 1 plus 1 squared times 1 equals 4. Okay. Um, However, there's a special rule when you're dealing with these broken up components in that they don't equal the order of the point group, but instead they equal 0. So I call that special rule 5 in my character table rules when I go over that. But what this means is that 1 times 1 squared, the first one is coming from the number of symmetry operations in identity. There's only one. And then I'm taking this character and squaring it plus one operation in the S4 class times a squared plus 1 operation in the C2 class plus -1 squared plus 1 operation in the S43 class times c squared. Okay, all that is going to be equal to 0. That's what our rule says. So in other words, this turns into 1, this turns into 1, and so 2 plus a squared plus c squared equals 0. And so a squared plus c squared equals -2. Okay. Now, what else can we do with the system of equations that we have? We also have a system of equations that tells us that b equals -1 here. So if we plug in -1 to this equation here, well, we'll get 1 plus -1, that goes away, and now we just have a plus c equals 0. So in other words, c we can write as equal -a, then we can plug that in here, sub in for c, -a, and that gets us 2a squared equals -2, a squared equals -1, a equals the square root of -1, which is the definition of I, the imaginary number. So now we can plug in for here, a equals I. And then we can continue and just plug in here, c equals -a. Well, that means c must be equal to -I. So right here is going to be -I. Now, something to note here, we know that 1 plus 1 equals 2, -1 plus -1 equals -2. So I plus d must be equal to 0. That tells us d equals to -I right here. And same thing here. -I plus f must equal what we started with. So we're decomposing it equal to 0. So f equals +I. And there we have it. We pretty much derived the entire character table. The only thing we have left to do is come up with the Mulliken symbols, which in this case is quite straightforward. We use the values a or b for Mulliken symbols when we have a dimensionality of 1. Okay, so for these first two, they're going to be an A or B, and if we're symmetric with the principal rotation axis, we give it an A. The principal rotation axis here is the highest order rotation that we have, highest order n, which is 4, so S4. So we give it an A here because we have a positive 1. Here we give it, why do we give it an A or B? Because there's a 1 here under identity. We give it an A because it's a positive 1 here. We're going to give this one, we're going to call it the vector B, because we have a positive 1 here, so it's A or B, and we're anti-symmetric with the principal rotation axis, so we get a -1. Here we had a 2, it kind of came from a 2, so this one together we call it E. And there we have what we derived, the S4 character table. Here are the 3 irreducible representations. Really, it's 4 irreducible representations. You can see here there's actually complex functions, x plus iy and x plus x minus iy, that's another way you can derive these. that give you this total sort of x comma y function, okay, where we add these two up and we got 2, 0, -2, 0. So these ones with complex values are always a little bit more interesting, but this was a fairly simple example, and we're able to drive it fairly quickly.